Good evening, and we're back for more specialist maths. It's going to be extra special today. We're looking at modelling some motion with variable forces. So no one constant force, and it's going to depend on the motion itself. And then we're going to look at forces acting on in two dimensions, not just straight lines, but other directions as well. We're going to use vectors to do that. We're going to be doing a little bit of differential equations, and we've got this really good one, which is kind of a bit of my favourite. So we're going to look at some steps behind it and what's important for you guys to be able to know and do yourself. Solving differential equations, in particular determining functions of motion. What is an equation of motion? What do we mean by that? And apply a bit of vectors to it. Alright, please note some homework exercises that are important for you to look at and to practice. Okay, alright, let's get to it. So first off, we've got the idea of a variable force. A variable force is force that depends on another parameter like time or position or maybe even velocity. Okay, so starting with Newton's second law. There's second law there. F equals ma. We have all the resultant forces. That is your resultant force. And sometimes we can draw on different versions of acceleration as a vector. We can have it as dv dt. Or if we're looking at the position vector, we've got the second derivative with respect to time. If we want to start eliminating time and represent it in a different parameter like displacement, we can use this one. And this is a useful one that we're going to draw on mostly today. What's important to consider is when we're using this version, we need our function of force. The acceleration needs to be some function of a parameter like velocity. Okay? And initial conditions need to be given in terms of displacement and velocity as well. So here's an example. Force given by V equals half V squared. Okay, so we've got this force and it acts on a particle of mass 1 kilogram traveling in a straight line. We need to come up with a rule. Express V in terms of x. Okay, so start with Newton's second law, and this is where we all begin. This is like the fundamental crutch of it all. Start with Newton's second law, and first express it as V as mass times acceleration. But hang on, we've got time here. We want different rate of change. We want to express acceleration in terms of V times dv dx, and we can obtain that using some chain rule relationship. And from there, let's go ahead and integrate both sides. 1 on v, dv is given by a half integral of dx. We get a log, okay, and so on. And taking the exponential to both sides, we get this nice expression. V is going to be greater than 0, perhaps. And we can finally get that as a general solution. Okay, and a is just the exponential of our c parameter here. Okay, very good. So this is the general example and the process what we're going to be doing with working with our variable forces. So let's look at an everyday example. Imagine you guys, you're walking down the street. It's a nice casual day in Tarneet, and you're trying to get home, and then all of a sudden something falls from the sky and it's going to squash poor Wesley. In trouble. Dear me, what's happened to poor Wesley? What are we going to do about that? Well, Mr. Elephant here, bit of falling out of the sky routine. What's happening to him? Well, he's got a bit of mass behind him, doesn't he? It's got a mass. And anything that has mass that is falling in the sky, falling under gravitational field, is going to experience a weight force, pulling it towards the ground. Okay, so there's the elephant's weight, mass times gravity. And then what happens? Well, is there any other force acting on our elephant as he falls? It might be a force that is opposing his motion, going up against as he falls down. And we generally call this force due to air resistance. Okay, yeah, there's a number of different rules we could have as the force due to air resistance. And it is always opposing our motion. So if we're falling down, then the force due to air resistance is pushing back up. And it depends on velocity of how fast the object is falling down. So as the object speeds up more and more and more, then it's getting even more force opposing its motion. And normally there's some parameter k multiplied by the velocity there. And this parameter here basically is in charge of things like the drag that the elephant experiences as it falls through the atmosphere. Could be in what affects the amount of force it will experience, could be the shape of the elephant, the texture of the material, the density of air itself, and so on. But what's important for our purposes is just knowing that it's a function of this type. So this is like a linear air resistance. We could also have quadratic air resistance as well. And our quadratic air resistance is of the form negative kV squared. Okay, both are acceptable. All right. So let's just squash Wesley one more time. Very good. So let's consider what it means to be falling under air resistance. Here's our particle model. We're going to consider just the particle experiencing two forces, one down, one up. So the sum of all our forces, mass times gravity, is the weight force going down. And because we're travelling downwards at some velocity, we're going to have down as positive value. Okay? So an opposing force is going to be negative, minus kV squared. Okay? And all those forces must sum to give you mass times acceleration. So what we have formed there is called an equation of motion. And what we like to do is take advantage of this equation of motion. And that's what Mr. Kitty does. Mr. Kitty is very clever because Mr. Kitty spans his legs out and arms out in a way to increase his surface area. And as he increases his surface area, what happens is that he's making this force, opposing force that's slowing down his motion, he makes that get larger and larger. And this force will keep increasing as well as the velocity increases up to some point. And this is the point where these two forces, being a subtraction, are going to balance. And it's going to balance to zero. We call that an equilibrium. Okay, an equilibrium is reached when the resultant force is zero. And that's an important statement, an important idea behind this type of problem. We're interested to know what is the velocity at this state of equilibrium. So we can see we've got the forces now equate to each other, and v squared is equal to mg on k. Okay, mg on k. Now this is an important quantity that we'd like to be able to identify, and we're going to give it a name. We're going to give it a name, and we're going to call it the terminal velocity. Terminal velocity is basically your maximum speed, the speed that you're going to go up to and not pass. Okay, and this is when the forces are balanced and you're now traveling at a constant speed. It is a constant speed because the acceleration is zero. Okay, and we're going to denote that terminal velocity as v with a little subscript t. We're going to want to try and look for this one as we're doing our working out of our equation. Okay. Okay. So let's come back to our elephant problem. We want to see what is the effect on the motion. What kind of differential equation we're going to end up with. What will be some solution, some general solution we can formulate from such a differential equation. We might have an overriding question such as, well, what is the velocity when Mr. Elephant hits the ground? Okay? Just in case we want to save someone's life. So let's start with F equals ma. It's a good place to start, and we always like to start there. Newton was very smart with this one. Alright, so we'll put in our forces. Weight force pushing down and the force due to air resistance pushing back up. And we make that equal to dv dt. Now, if we don't know anything about time in this problem, and we want to adjust it, maybe we can change our dv dt to be something else. Alright. Let's make here, what was done is, we can see, well, dv dt, that's the same as v times dv dx. Okay? And then we've started to rearrange this right-hand side here. I've got this factor of k on n that we took as a factor and we factorized it out on the right-hand side. Okay? And we've ended up with this mg on k term right here. Now that might be useful to recognize what is that term the same as. And in fact, mg on k is the square of the terminal velocity. And conveniently, I'm going to use that as the parameter because this is like my equilibrium solution, and it's popping up inside my workings out of my solving my DE. And also my K on M, if I just by rearranging that a little bit, I've also got that's equivalent to G on VT squared. Okay, so let's continue. We've got then a bit now where I'm going to separate my dV and dx and put all the v terms to the left hand side. So that's this bracket here that's got my v term, my v squared in it. I'm going to divide that to the left hand side and I'm going to multiply my dx to the right hand side. So I can then start to integrate both sides of the equation and I can have a look and I think, well, I know the shape of this, the structure of this type of integral. I'm going to use substitution method. So I let the denominator equal to u and then I work out du, dv and get this amount here. And I keep going. I then transpose that for a function of du, so I can do a substitution. Substitute that all into the expression. And now I've got an integral of 1 on u, and I've got my negative half out the front, because it's just a constant, doesn't take part. And on my right, I've got, when I integrate, I get an x plus c, and I can put all the plus c's there together. And 1 over u, the integral of that is a log function. And so I'll have that log there, and when I substitute u back in, my u is the v squared minus vt squared minus v squared, and I'll have this nice thing. So I'm up to this part and I'm considering, well, that's pretty good so far. What do I know about the argument inside the modulus here, vt squared minus v squared? Well, the first bit, vt squared, that is my terminal velocity, and my terminal velocity is like my maximum speed, the maximum velocity that I'm going to achieve. So if I have my maximum and I subtract some other velocity, which is not the maximum, that's going to always be positive, isn't it? So the modulus of a positive number is going to stay positive. Don't really need that modulus there now, do I? So let's come up to here now and see what is next. There we go, I don't need the modulus. It simplifies things a lot, in fact. Now, if I have the situation where Mr. Elephant is jumping out of a plane, perhaps, maybe. He's falling from some high position above the ground, from rest. So here's some conditions I've got at when v is 0, okay, meaning at some rest position, I've got some initial height, okay? So using that, I'm going to substitute that in, I'm going to work out what c is. And nicely I'll have vt squared minus v squared, where when v is 0, just gives me the log of vt squared. Nice simple expression there. Solve that for c. Then I substitute that back in and apply a bit of log rules. And when I apply the log rules, I get to have all the v's and the vt's together. It makes it nice and compact and neat. Very good. And then I've got my common factor of 2g on vt squared, which I can factorize out. And I've got this expression here, this x minus x naught. Some final position minus the initial position. What's that all about? Well, I can hear what you're saying. That's displacement, sir. You're right, it is displacement. Okay, so let's call that something else. Call that s perhaps. So we've got our displacement x, and when I take the exponential function to both sides, I get this expression. It looks pretty good. And then finally, the last job is let's go ahead and transpose for v, and I can do that nice and quick on the CAS as well. All right, let's see what we get. Square root of 1 minus an exponential function. Looks pretty. Now let's have a see what it looks like on the graph. Let's do a velocity versus displacement graph of this object falling under air resistance. And here it is. Starts at some initial position away from the ground, and then velocity versus displacement. So first off, picks up speed nice and quick, and then the speed kind of plateaus out. And we get this asymptotic type behavior now at this value. I wonder what that value is. Have a guess. What is some maximum speed? There we go, it's your terminal velocity value. Okay? V equals our terminal velocity in there. And that's equivalent to the mass times gravity, which is the weight force, divides some air resistance proportionality constant. Okay, and this is that determines the drag force. Okay. Now, what is the velocity when it hits the ground? So, when does it hit the ground? Let's say Mr. Elephant was 10 meters high off the ground, or even higher, let's say 100 meters high. 100 meters is probably at the end of the diagram. Some distance above the ground. So given that point, we substitute that into our rule, and we can evaluate, and we can get our answer. Alright. Okay. Find the velocity v in terms of distance above the ground x of a particle of 2 kilograms in mass. So we'll start to note things down. 2 kilograms. Falling under gravity of 10 meters per second. Okay, g equals 10 meters per second squared. And experiencing quadratic air resistance with a force given by that. Nice equation. 0.5 v squared. What is the speed of the particle when it impacts on the ground if it fell from rest from some height 100 meters above the ground? Okay, and then once we've done that, what proportion of maximum velocity is reached upon impact? And proportion, keyword, is like a percentage. Okay, so start with Newton's second law. All the forces are going to sum together to give you mass times acceleration. And the forces involved are, we've got mass times gravity, that's your weight force, force pulling it down, minus k times v squared is equal to mass times acceleration. Okay, weight force pulling down, quadratic air resistance pushing back up, and gives you your resultant force. Let's plug in our values. Mass is 2, g is 10, and so on. K is 0.05, which is a 20th. Let's express dv dt, not in dv dt, but as a function of x, because I'm interested in what is the velocity as a function of distance, in terms of distance. Okay, and divide by 2. I've got this fraction of a 40th. I'm going to factorize that out, and now I get 400 minus v squared. Now that 400 is, if you relate it to the previous problem, is the same as our terminal velocity squared. So it can tell you a little bit about what is the terminal velocity. Okay, now let's bring all our v terms together and bring our dx to the other side. And when we integrate, we notice v squared is, the terminal velocity is 20. Now, here we have, integrating gives you a log function. And we have our x minus x naught, which is the same as our displacement. And when we take the exponential on both sides, we get that expression. This is like the example we did before. And finally, we get our function for velocity by transposing for v and taking the square root. Okay, so that's what was happened in this step. We get to transpose for v. Alright, so there's our velocity function. Let's look at now the bit where what is going to be the velocity of impact, say 100 meters off the ground. So when 100 meters has passed as the displacement from where the objects start, we get that value, 19.9 meters per second, which is approaching the terminal velocity speed. Now, what is that as a proportion of the maximum velocity? By expressing our determined velocity as a fraction of terminal velocity, 19.9 out of 20, v over vt, then we get our proportion, 99.5%. So we're almost at the maximum. All right, what do you think? Okay, let's try another one. So now we've got a body of mass 10 kilograms initially at rest. Okay, that's a good thing. It reminds me, initially at rest means initial velocity is about 0 when t is equal to 0. And we've got that acting on by a force, F equals 10 minus t all squared, newtons, at t seconds, where t is given by this domain. Okay, find the speed of the body after 10 seconds and the distance travelled. Alright, so where do you think we should start? We should start with one of those rules. Which one was it? Use Newton's second law. Okay, fundamental beginning. all the sum of forces summed together to give you mass times acceleration. So mass times dv dt, and I'm going to stick with dv dt now because I want a rule. I know my forces in terms of time, and I'm interested to know what is the force at some point in time. Okay, now by multiplying my dt to the other side and integrating, I get this. I set up my integral on my right hand side. I'm going to use a bit of a substitution rule, and I'll have a negative out the front, and I'll get a solution like that. There's my first equation. Now I'm going to draw on my initial conditions. Initially at rest, at time equals 0, I get an initial velocity. Substitute that in, and I can solve for my c constant. And I can simplify that a little bit, put that back in, and I can factorize some common factor of 1 over 30 there. Get a nice expression. So from that, I'm now interested to know, well, what's the speed of the body 10 seconds after it's left? So when is t equals 10? Substitute that into my equation, and I can get a value. It's about 33.3 meters per second. Okay, what is the distance traveled? I have to integrate that again to work out a rule for displacement as a function of time. So my v is dx dt, and then by integrating to get x, a function of x, I've got now two terms that I have to integrate across. And the integral will give me this as a rule. Okay, try it yourself to make sure that you are able to do that main step as well. And one thing I have to also remember is my integrating constant. Each time I integrate, I have to have an integration constant. There's my initial conditions. So at some point in time, I have some starting position. It's like an origin. Okay, x equals 0 is like an implicit initial position. When time is 0, x is 0. And if it's not explicitly stated otherwise in the problem, always need to assume that when time is 0, the position is 0. That's some starting point of origin. So I'm going to plug that in, and I get a value for my integration constant d. Check for yourself if you don't believe me. And there's my position rule. Okay, all together. Now, what is the position when time is 10 seconds? I can substitute that in and evaluate, and I get my result, 250 meters. Very nice. So now we're going to look at some motion that's occurring in 2 dimensions. And we're going to introduce vectors into all this. But don't worry, it's not that scary. It doesn't complicate things too much. It just means we've got, instead of one big problem, we've got 2 little ones. 1, 2. Let's try it. So here's our force. We're going to express it as some x component the I direction and some j component as well. You can determine velocity and position from a resultant force vector, and we're essentially solving now 2 differential equations. One for I, one for j. Okay, let's try our example, shall we? So a resultant force acting on a particle initially at a velocity of v equals 2I. Okay, so instead of some initial velocity on its own, it's now just going to be given in vector form. So that's just highlighting the fact that it's going to be in the I component, the I direction. And here's our force acting on the particle. It's just 2 linear functions, one in the I component, one in the j component. Let's determine the displacement of the particle at 2 seconds. Okay, all right. So use Newton's second law. We've set it up where we'll make the force equal to mass times acceleration. And now our v for velocity is not a normal velocity, it's now going to be vector velocity. And to work out the vector function, we have to integrate the right hand side to both sides. And when we integrate, we get now these quadratic factor expressions for one in the I component, one in the j component. Using our information, when initially at rest, which means t equals 0, our velocity is given by this vector. And when we substitute that in, all my t's will go to 0, and I'll have my t vector I is equal to c I and dj. And from that, by equating my I components and equating the j components, I get my values for each integrating constant there. Let's substitute that into the rule and I get my particular solution in vector form. Now let's integrate again, and that will give me position. Okay? So upon integration of each term, I get now cubic and quadratic equations. And I must have new integrating constants as well. Now this time, because it's a position function, when time is 0, what's going to be the initial position? Okay? And unless it's explicitly stated in the problem, we're always going to assume that the initial position is going to be 0 at some origin or original position. And we get our values for integrating constants by substituting that in. And finally, there's our complete position vector. Now, if I'm interested in something like the distance traveled or the displacement of the particle, I'm going to get my displacement in this manner. Okay? Ooh, that's better. It's the modulus of each. Okay, the modulus of the position at time equals 2 seconds minus the modulus of the position originally. Okay, and I substitute that in and do the modulus of each vector that I get, and I'll get my result. Very good. Okay, now we'll do one more problem. Let's consider what is the size of the resultant force acting on a 2 kilogram particle with a position vector given by this. And we want to know, well, what is the resultant force when t equals 1 second? So now we're working backwards. We started with position vector and we have to determine what the force is. So we're looking at the rates of change, which is differentiation problem. So we start differentiating. First we get the velocity vector, taking the derivative of each, okay, and keeping them all separate and keep them within their I and j component. And we differentiate again. Second derivative of position is acceleration. That one's velocity. Okay. And then once I got my acceleration, I'm going to multiply my acceleration by mass. And that will give me mass times acceleration, which is the same as force. And that's my resultant force. Mass times acceleration as vectors. Okay? Once I get my function, substitute my value for t in and I get my vector of a resultant force. And then the modulus gives me my size. That's the size of the force. Okay? Very good. That's a nice straightforward one, but it's important to see that we can apply the calculus in either direction for these types of problems. Okay.